Deep dive into sklearn Linear Model, Lasso Lars. The sklearn Linear Model, Lasso Lars model implements a linear model trained with the Lasso least absolute shrinkage and selection operator regularization using the least angle regression Lars algorithm. Let's break down its components. Core concepts. Lasso regularization. Lasso adds a penalty term to the loss function proportional to the absolute value of the coefficients. This encourages sparsity in the model, meaning many coefficients are shrunk to zero, leading to feature selection. This is particularly useful when dealing with high-dimensional datasets where many features are irrelevant or redundant. Lars algorithm. Lars is an efficient algorithm for solving the lasso problem. It works by iteratively adding features to the model, selecting the feature that has the highest correlation with the residual. The algorithm stops when the desired level of sparsity is achieved, or the maximum number of iterations is reached. YAML breakdown. Name Lasso Lars. Description. This is a concise summary of the model, stating that it's a linear model trained using lasso regularization with the Lars algorithm. Class. The full class path within scikit-learn library. Parameters. Alpha. This is the key parameter controlling the strength of the L1 penalty. Higher values of alpha lead to stronger shrinkage and more sparse models. The default value is 1.0. You can tune this parameter using techniques like cross-validation to find the optimal value for your data. Fit intercept. Controls whether to include a constant term intercept in the model. Default is true, adding a bias term to the linear model. Set this to false if you are sure that the model should pass through the origin. Normalize. Determines whether the feature columns should be normalized before fitting. Normalization involves subtracting the mean and dividing by the L2 norm of each feature. This can improve the performance and stability of the model, especially when features have significantly different scales. Defaults to false. Precompute. This parameter controls whether to precompute the gram matrix XTX. Precomputation can significantly improve performance when working with large datasets. Defaults to false. Maxiter. Specifies the maximum number of iterations the Lars algorithm will run for. Default is 500. If the algorithm doesn't converge within this limit, it will stop and issue a warning. APES. Controls the precision used in the Kolsky factorization. A smaller value results in more precise computation but might lead to slower performance. Default is 2.220446049250313 times 10 to the minus 16. Copics. Determines whether the input data X should be copied before fitting. Setting this to true ensures that the original data is not modified. Defaults to true. Verbose. Controls the verbosity of the model during fitting. A higher value prints more information about the progress of the algorithm. Default is 0, meaning no output is printed. Positive. Forces the coefficients to be positive. Defaults to false. This can be useful if you have prior knowledge that the coefficients should be non-negative. Random state. Controls the randomness introduced in the model, particularly when shuffling the data before fitting if warm start is false. Defaults to none. You can set it to an integer for deterministic results, a random state instance, or none for default random seeding. Warm start. Determines whether the solution from the previous fitting should be reused as the starting point for the current fit. Setting this to true can speed up fitting, especially when the data or parameters change slightly between calls to fit. Defaults to false. Attributes. Core the array containing the estimated coefficients for each feature. Intercept the estimated constant term of the linear model. Niter the actual number of iterations performed by the Lars algorithm during fitting. Active indices of the features that were selected by the algorithm non-zero coefficients. X the raw input data used to fit the model. Y the raw target data used to fit the model. N features the number of features in the input data. Alpha the value of the alpha parameter used in the fit. Epsilon the value of the epsilon parameter used in the fit. Positive the value of the positive parameter used in the fit. Maxiter the value of the maxiter parameter used in the fit. Copix the value of the copix parameter used in the fit. Precompute the value of the precompute parameter used in the fit. Normalize the value of the normalize parameter used in the fit. Fit intercept the value of the fit intercept parameter used in the fit. Methods. FitX. Y fits the Lasso Lars model using the provided data. PredictX predicts the target values for the given input data. Score X. Y calculates the coefficient of determination R2 on the given data, indicating the goodness of fit. GetParams returns a dictionary of all the parameters of the model. SetParamSquarks sets the parameters of the model using a dictionary of keyword arguments. Applications. Feature selection. Lasso Lars can be used to identify the most relevant features in a dataset, leading to simpler and more interpretable models. High-dimensional data. It's particularly useful for handling data with a large number of features, as it can effectively handle collinearity and reduce overfitting. Sparse models. Lasso Lars produces sparse models by shrinking many coefficients to zero, making the model more interpretable and less prone to overfitting. Signal processing and bioinformatics. These fields often involve high-dimensional datasets with a limited number of samples, making Lasso Lars a suitable choice. Example. Python. From sklearn, linear model import Lasso Lars. From sklearn, datasets import make regression. From sklearn, model selection import train test split. Generate synthetic data with 100 features and 100 samples. X, Y make regression samples 100. N features 100. Random state 42. Split the data into training and testing sets. X train, X test, Y train, Y test train test split X, Y. Test size 0.2. Random state 42. Initialize and fit the Lasso Lars model. Model Lasso Lars alpha 0.1 set alpha for L1 penalty. Model. Fit X train. Y train. Make predictions on the test set. Y pred model. Predict X test. Evaluate the model. Print FR2 score model. Scores test. Y test. This example demonstrates how to use Lasso Lars to fit a model, make predictions, and evaluate performance. Remember to adjust the alpha parameter based on your specific data and requirements. In conclusion, sklearn, linear model, Lasso Lars offers a powerful and efficient way to perform linear regression with lasso regularization using the Lars algorithm. It excels in scenarios requiring feature selection, handling high-dimensional data, and building sparse models. By understanding the core concepts and parameters, you can effectively leverage this model to improve your machine learning applications.